Các em thấy được màn hình của thầy chưa?
Được hết.
Okay. Các em nghe được lời giảng của thầy chưa?
Không nghe thầy ơi.
Không nghe. Okay, so we will now consider how we các em nghe được chưa? Lời giảng của thầy.
Dạ rồi thầy ạ.
Okay. How can we apply this two-step analysis procedure to calculate the important parameters for different configuration of amplifier using BJT? So the first important configuration is a common emitter, so or CE. So you can see here the input signal here, modelized by a Thevenin equivalent circuit, is connected to the base of the transistor. The output signal is taken from the collector here to supply to the load R3. Okay, so the emitter terminal here is common for both the input and the output, and that's why we call common emitter. Okay, the first step, DC analysis is very simple, so we not consider that. The second step is the AC equivalent. Okay, so we replace coupling capacitor and bypass capacitor here by short circuit. Okay, then we redraw the circuit to have the AC equivalent circuit. So RB here is indeed R2 in parallel with R1. RL here is what is connected between the collector and the ground. That means RC in AC mode, VCC is connected to the ground. C2 is short circuit, so we have R load is RC in parallel with R3. Okay, and RE. Okay, so RE here in this case, if we have a C3 here, so RE is bypassed, so emitter is connected directly to the ground. Okay. For a Spencer configuration, we don't have a RC3 here in all, so that means RE is still present here. Okay, there is another Spencer configuration with RE is the feedback resistance to stabilize the amplifier. We will talk about that advanced configuration later. For the moment, C3 is short circuit and RE is bypass, and that means emitter is connected to the ground. Okay. So the calculation is here, nothing complicated. So now we will replace the transistor by a small signal model so that we can have the complete AC equivalent circuit, and then we can calculate on parameter. So that is for common emitter. The second most important configuration is a common collector. Okay. So for this common collector, again, the signal source modelized by its Thevenin equivalent here is connected to the base, right? The output here, the load R3 here, the output here is taken from the emitter. Okay, of course, on way through the coupling capacitor C3 here and supplied to the load. So the collector here is in common. We have that common collector. Okay, so here is the AC equivalent. Okay, so in AC mode, C1 is short circuit, C2 is short circuit, C3 is short circuit. So you can see here, if C2 is short circuit, the collector is immediately connected to the ground. Okay, so the base is connected to R2 and R1 in parallel to the ground. So we can combine it to RB and connect it to the input signal here, right? And at the emitter is connected to R6 to the ground, and R3 to the ground. So R6 and R3 is in parallel, and we combine this as RL. Okay, so RL is in R6 and R3 in parallel. Okay. For common base configuration, you can see here the input signal here is Thevenin equivalent. The input signal is supplied to the emitter, is connected to the emitter here. The output signal is taken from the collector here through the coupling capacitor C3 to supply to the load R3. Okay, so the base is in common. So that we call that common base or CB. Okay, how to draw the AC equivalent circuit? Okay, so you can see here for AC we replace a capacitor by short circuit, so C2 by short circuit, C3 by short circuit here, C1 by short circuit here. So you can see here at the base, okay, so the base C1 is bypass, VCC is connected to the ground also. So at the base here, the base is connected to R2 and connected to the ground. Okay. B, if C2 is short circuit to the ground, then B is short circuit to the ground. Okay. So B base here is connected to the ground. Okay, short circuit to the ground. How about the emitter? The emitter is here, is connected to R6 to the ground and connected to the signal source. So emitter is here, connected to R6 to the ground and connected to the signal source here. How about the collector? The collector is connected to C3 and connected to R3 and connected to the ground and connected to RC and connected to the ground. So that means RC and R3 is in parallel. We combine it into RL. Okay, so RL is RC in parallel with R3. So we have the IC equivalent circuit. Okay, so now we will combine for this AC equivalent circuit for common emitter, this here, AC equivalent circuit for common collector, AC equivalent circuit for common base. We just replace the transistor by a small signal model, and we have the completed AC equivalent circuit. And we can calculate all parameters of the transistor. Okay. So now we will consider in detail the very first important configuration is the common emitter amplifier. Again, signal source here, Thevenin equivalent, connected to the base. The output is taken from the collector and supplied to the load R3 here. Okay, the transistor is biased by the 4 resistor biasing network in the middle here, right? Okay, so here is the AC equivalent circuit that we have considered so far. We combine it here as RL. Okay. Then we replace the transistor by a small signal model here. Okay. Again, you can see here between the base and emitter is R pi. Between the collector and emitter here, you have the output resistance R0 and the current source, which is equal to Gm VBE. VBE is the AC voltage between the terminal B and the terminal E here. Okay, and it's also the voltage drop of the input resistance R pi. Okay, so we combine everything that is connected between the collector and the ground here. All of that we call the load, the output load of the amplifier. We call that RL. Okay, so RL in this case is equal to R0 in parallel with RC in parallel with R3. Normally, R0 is very big compared to RC and R3. So normally, in most of the case, we can omit R0. Okay, so that we can have a RL approximately equal to RC in parallel with R3. Of course, for some cases, if R3 is large, for example, R3 is 100 kilo ohm, RC is 50 kilo ohm, then R0 100 kilo ohm, you cannot omit R0. But in most of the case, because in the biasing circuit here, the current IC here is in the order of milliampere. The voltage supply here is in the order of volt. So RC here is the order of kilo ohm, or as maximum tens of kilo ohm. So that means it's lower than R0 here. Okay, so normally we can omit R0. Okay. So now we will consider the small signal AC small signal equivalent circuit of the transistor here in order to calculate Vout. That means the voltage on the load R3. If we know Vout, then we can deduce the voltage gain AV equal to Vout over Vi here. Okay. We should calculate also the current IOut here and the current input current I in here, so that we can deduce the current gain IOut over I in. Okay, so if we know AV and AI, we can deduce AP, of course, the power gain. We can calculate also the input resistance here. Okay, seen from the signal, so you can see immediately that input resistance is equal to RB in parallel with R pi. Okay, so it's very easy to see. And R out here. R out here is the output resistance. So seen back from the load here. And you can see immediately that R out is equal to RC in parallel with RO. Okay, so it's quite easy with this circuit. R out in parallel with RC. R in here is RB in parallel with R pi. Okay, normally RB is very large. Okay, you can see here R2 is 100 of kilo ohm, R1 is 100 of kilo ohm. In order to limit the current here at the input is just in the order of microampere. You know that the IB is in the order of microampere only. So the current, so the resistor R2 and R1 here is the order of 100 of kilo ohm. So that means RB here is also in the order of 100 of kilo ohm. RP here, R pi here, R pi, you know that is equal to B0 over Gm. So B0 is about 100, Gm is in order of millisiemens, 40 millisiemens for example. So R pi here is the order of 2 to 5 kilo ohm, for example. So you have something very big, 100 kilo ohm, in parallel with something small, R pi in the order of kilo ohm. So that means R in here is determined mostly by the smaller one. Okay, so that means determined by R pi. And in turn, R pi is determined by the transistor itself. That means the beta 0 and the current of the Q point. Okay, because Gm is 40 IC. Okay, so very interesting. The macroscopic behavior of transistor of the amplifier in this case depend on the parameter of the transistor itself. Okay, both the intrinsic parameter of transistor, that means the DC current gain beta 0, and the external circuit parameter of transistor, that means the Q port, the current I see here. So you have many way to control the parameter of the amplifier by controlling the internal parameter, that means by selecting the transistor to have the beta 0 that you want. And if the beta 0 is given, you can have another freedom to control R pi is by controlling the current IC, okay, or by a sync circuit. The other R here is again R0 in parallel with RC. Okay, so we are trying to analyze for the calculation, nothing complicated, because you have a formula here. I have explained on to you. Just apply the formula, nothing complicated. But we are trying to analyze the meaning of the equation. So the output resistance here. So don't forget that we want to have R in very big. But R in here is limited by R pi, and R pi is in the order of 2 or to 5 kilo ohm, for example. That means the drawback of the common emitter amplifier is that the R in, the input resistance, cannot be very big, okay? But it's limited by R pi. That means it's limited by beta 0 and IC, okay? How about the output resistance? The output resistance is R0 in parallel with RC. Okay, so R0 here is VA. Don't forget that R0 is VA over IC. So VA is order of 100 volt. IC here is the order of milliampere. So that means R0 is in the order of 100 of kilo ohm. And RC you can see here is quite small than R0. So you can see that RL is determined mostly by RC, okay? So, and it is in the order of kilo ohm. So that means the output resistance of the common emitter circuit here cannot be very small, okay? So don't forget that for a good amplifier, we require that the output resistance must be very small, okay? RL should be small. How about the gain, okay? The gain here is including the voltage gain, okay? So you can see here, we can we can further simplify this circuit by combining everything connected between the collector and the ground here will be the load, and we call that RL. Okay, so RL here is R0 in parallel with RC and R3 here. And we can deduce immediately that the output voltage, that means the voltage on the load, VL here, is simply the output current here, IL, multiplied by RL. And IL is equal to minus IC here. And IC here is GM VBE. Okay, so we will calculate together here in order to deduce the voltage gain. Now another gain you can do that at home. Okay, so here VL is here. VL equal to IL RL. IL is equal to minus IC. So minus IC RL. So minus IC, that is this current, is equal to this current source. Okay, there is GM VBE. So minus GM VBE RL. Okay, so we know VL. Okay, so the voltage gain, we are trying to calculate the voltage gain. AV is equal to VL over VI. Okay. If we know to calculate only the terminal voltage gain, that means only VC here over VB is very simple, okay? Because VB here is equal to VBE and equal to VBE here. So you can deduce here from this equation, you can deduce immediately the terminal, the voltage gain at the terminal, so AVT. Sometimes they include common emitter here to indicate that it is for common emitter. Is equal to voltage at the output terminal VC, so VC divided by the input voltage and the input terminal, so that means VB. So it's equal to minus GM VBE RL. VB is here, so you can see that emitter is connected to the ground, so VB is indeed equal to VBE here. So VBE, and is equal to minus GM RL. Okay, so this is the terminal voltage gain. Now we have to calculate the total voltage gain. Okay, the total voltage gain is equal to the output voltage on the load, so that means VL over the input signal, so that means VI. Okay, so now, so we have V out is minus GM VBE over RL. So we have to relate back VBE to VI. So in order to divide it VO, V out by VI. Okay, so what is VBE? VBE is the voltage at this point. Okay, so there is the voltage drop on RB in parallel with RB. Okay, so voltage at this point, in fact. So if you combine RB and R pi together, add a resistor, so you can combine. This is in fact also the R in the input resistance is equal to RB in parallel with R pi. So you can see that VB is the voltage drop on this R in. You have a 1 voltage source and 2 resistors in series, RI and R in. So VB and VBE is the voltage drop on R in. So VBE is equal to VI multiplied by R in over RI. RI here is the internal resistance of the signal source. For some textbook indicate Vs, okay, for the signal source, and plus V in. So you can combine the first equation and the second equation here, okay, and you can deduce immediately. So you just replay here VBE here to V out and then divided by V in, cancel out V in. So the voltage gain here is equal to R in over R I plus R in, okay, and multiply by minus GM RL. Okay, so this is the total voltage gain, right? So you can see here that this is the total voltage gain. Similarly, by applying the Kirchhoff current law, Kirchhoff voltage law, you can calculate the current I out here, which is equal to simply V out over RL. You can calculate the current I in here, which is simply equal to VI divided by RI plus R in. Okay, and then you take I out over I in to have the current gain, IE. Okay, AI. Okay, so from voltage gain AV, from current gain AI, you can deduce the power gain. Okay, AP. Okay, so that means we know on parameter for this amplifier, common emitter amplifier. Okay, so again, it is the total voltage gain. Okay, the terminal voltage gain here is minus GM RL. Okay, as we have calculated before. Okay, homework. You should do this homework immediately. Okay, in order to to master the technique. Okay. So let's take an example here before we stop. Okay, so we have a real circuit here. Okay, just replace the number. Okay, so the Q point. Okay, from the 4 resistor biasing network here, we can calculate the Q point is so the current IC here, VCE is here. It's not really optimal. You can see here, the VCC is 12 volt and VCE is only 3.2 volt. It's not the midpoint point. Okay, the midpoint point. The output characteristic curve is here. The optimum working point for transistor is the midpoint point, that in the intersection with the x-axis here is the VCC, and VCEQ must be a half of VCC. That means if VCC is 12, VCE optimum is 6.1. Here is not really optimal. We will see about that later. If the Q point is optimum in the mid-tone here, that means the maximum output amplitude of the output signal is limited. Okay, but we will consider that later. So okay, so the Q point from 4 resistor biasing network, we can calculate the Q point. Beta F 100 is given, VA 75 volt is given. Okay, so from the step 1, the Q point is the step 1. So DC analysis, right? So you can find Q point. So from the Q point here, you can deduce the parameter. 3 most important parameter for the small signal of the transistor. That means GM is 40 IC and is 9.8 millisiemens. Okay. R0 is approximately, you can use the exact equation if we have a VCE here. So, but normally you can see that VCE is very small compared to VA. So you can approximate this by simply omit VCE, and R0 is approximately equal to VA over IC. So you can see here R0 is very high, okay, 300 kilo ohm. R pi is beta 0 over GM. Okay, beta 0 is beta F is 100. Okay, GM is 9.8 millisiemens. So you can see here R pi is 10.2 kilo ohm. Okay, so RB is R1 in parallel with R2. You can calculate here. RL is RC in parallel with R3 and in parallel with R0. So you can calculate here. So that is the RL. So the input resistance is the RB in parallel with R pi. You can have it here. Okay. So just replace on the parameter here. So you can see here the total voltage gain is the terminal voltage gain AVT here, which is minus GMRL and multiplied by Rin over Ri plus Rin. Rin is the input resistance and is equal to Rb in parallel with R pi. Okay, just replace the number here and you can see that the gain here is minus 151. The minus sign here, it just indicates that the output voltage is out of phase compared to the input voltage. Okay. So R in here. Okay, R in. Here is the wrong equation. R in have nothing to do with Ri. So R in here is just Rb in parallel with R pi. Okay, and is 10.2 kilo ohm. 10.2 kilo ohm in parallel with 104 kilo ohm. So you can see that something here is 10 R, here is R, so it's nearly R. Okay, so it's nearly 10 kilo ohm. Okay, it's about so R in is nearly 10 kilo ohm. Okay, so here we should check. Here there is we should check the condition for the small signal modem. Okay, so VBE is, as we have calculated before, VBE is equal to VI multiplied by R in over Ri plus R in. Okay, and you can see here we have a check here, and VBE if for the condition of small signal, VBE must be less than 5 millivolt. That means VI must be less than 5.5 millivolt. Okay, so that means this circuit work only in the small signal mode with all the parameter that we have calculated here is valid only if the input signal here satisfy the small signal condition. That means it must be less than 5.54 millivolt. Okay. So as a rule of thumb, when you calculate this common emitter, as the rule of thumb, the voltage gain of the common emitter is somewhere around 10 times VCC. Okay, 10 times VCC. Okay, so as a rule of thumb. So here VCC is 12 volt, 10 times VCC, that means 120 volt. The calculated value here is the absolute calculated value is 150. So it's okay. Okay, so it's okay. If you have here 300, or for some students they can go up to 1000, etc. So if you check with this estimation, you can see immediately that there's something wrong with your calculation here. Okay. Simulation result. Okay, at home you can simulate the circuit with LT Spice. Okay, for all of your homework here, after hand calculation, you can simulate with LT Spice to verify your hand calculation result. Okay, so let's simulate this circuit, for example. Okay. So I'm opening LT Spice. So normally it should be very quick, but I don't know why. It's updating the program maybe. Okay. Preparing library. So just remind you again that for all the homework that are given, so for example, on of this homework here, okay, so you can verify your hand calculation result by simulating the current, the circuit that you have calculated, and compare the simulation result with the hand calculation result. If the error is less than 10%, so that means in the order of the error for the resistor, so it's okay. Okay. If the error is less than 10%, you have to check your hand calculation. Okay. There might be something wrong with my LT Spice installation. Okay. So on the simulation file, I have shared with you on the online folder. Okay, so you see online, you can go see BJT Amplifier LT Spy here, and BJT Common Emitter Example 1, I think. Example 1. Okay. This one, BJT common example 1 here. So let's check the value. So power, let's check first. The power supply is 12 volt, and the signal source here, internal resistance in 1 kilo ohm, 300, 160. Okay, 12 volt, 1 kilo ohm, 300 and 160. Okay. How about RC22, RE is 13, and the load is 100. 20, 13, and 100. Okay. The coupling capacitor must be infinite. Okay. Normally it should be large enough so that at the frequency of the input signal Fi here, the ZC equal to 1 over 2 pi Fi should be nearly equal to 0 to be seen as short circuit. Okay, so here I have chosen the input signal is a sine wave voltage with the amplitude of 1 millivolt and frequency of 10 kilohertz. So F is 10 kilohertz. So omega is 2 pi 10 power 3. Okay, so if I choose the capacitor here is 10 microfarad. So I will check if 10 microfarad is enough. So again, the frequency here is 10 kilohertz. So in 10 power 4, 2 pi is nearly 10. So 10 power, so 2 pi f is 10 power 5, 10 power 5. If I choose capacitor here, coupling capacitor is 10 microfarad, that means 10 power minus 5. 10 power minus 5 multiplied by 10 power 5 is 1. So 1 over 1 is 1. So okay, so ZC is around 1. So it can be seen as short circuit. Okay, so the coupling and bypass capacitor here is okay. Okay, so I will check again. I will count this node is collector. I will count this node is base B. I will count this node emitter E, so that in the simulation circuit I can see the voltage at this node, because so I have to name the node. If no, the software will name the node by a number randomly. Okay, and we don't know what is the number corresponding to the node B, or what is the number corresponding to the terminal C, etc. Okay. So the first one is you should carry out the very first step, that is the DC analysis. That means you have to simulate the DC operating point. So you choose DC operating point, click OK, and then you run the simulation. Okay, so it will use the node voltage and mass current technique to calculate on the voltage on the node and on the current run through on the component here. So here we want to check the current IC. Okay, so the current IC of the transistor Q1 here, as you can see here, the standard unit is ampere. So in order to change it to milliampere, you have to multiply it by 1000. So 1, 2, 3. So 0.26 milliampere. Okay, so the hand calculation result here is 0.245. Okay, so you take 0.26 minus 0.245 here. So you calculate the error in 100%. So you multiply by 100 and divided by the true value here is 0.26, and the error is only 6%. So it's acceptable. Okay. How about VCE? VCE is VC minus VE. The simulation software don't calculate VCE, it just calculate the voltage on the node. But we know that from the voltage on the node, we can calculate any voltage between two nodes. So VCE is the voltage difference between the node C and the node E. So you take voltage at the node C here minus the voltage at the node E here. So you have a 6.24 here, 24 minus 3.42. Okay, 3.42, and it's 2.82. The hand calculation here is 3.39 minus 3.39. Then you multiply by 100, then you divide it by the true value here is 2.84, I think. Okay, the error is very large, 20%. Okay, so what is the problem here? Okay, let's check here. Normally that is the parameter of the transistor. Okay. For this transistor, the beta F, the DC current gain beta F is 200. Okay, but in this example, we take beta F is 100. Okay, so that's why the error is very high. So I should choose a transistor with beta F is around 100 to have the simulation more accurate. Okay, beta F 100. We choose a transistor with beta F. Okay, I can use this transistor For example, it's the same time NPN with beta f is 120. So 120 and 100 is not far. Okay. So I run the simulation again. You can see here the results for IC is more exact. Okay. Now the simulation result for IC is 1, 2, 3, 0.25, okay, here 0.25, okay, minus 0.245 multiplied by 100 and divided by 0.256. The error for current IC is only 4%. Okay, it's acceptable. How about VCE? VCE here, you take VC, which is 6.37, okay, minus VE is 3.35, okay, and it's 3.02, okay. So the hand calculation here is 3.39, so it's minus 3.39 multiplied by 100 and then divided by 3.39, and the error is around 10%. So, okay, so it's okay now. Okay. So DC analysis, okay, verified by DC simulation. Now AC analysis. So you should choose transient here. Okay, so transient. So the frequency of this sine wave is 10 kilohertz. That means the period is 1/10 kilohertz is 1/1 kilohertz is 1 millisecond, and divided by 10 is 0.1 millisecond. So normally we should simulate for 100 cycles of this sine wave. So 100 cycles, that means the time is 100 multiplied by the period is 0.1 millisecond. It will be 10 milliseconds. So I will simulate for 10 milliseconds only. It's enough. Okay. So then I will run the simulation. Okay. Now I should check. I should display something that I know for sure first to check. Okay. So the most the most certain voltage that I know is the input voltage. I know that is must be a sine wave, frequency of 10 kilohertz and amplitude of 1 millivolt. So that I use this voltage probe to display. Okay, so you should make a zoom. Always make a zoom to verify the form of the signal, right? So there is sine wave with the amplitude here. The maximum here is 1 millivolt, and the minimum here is minus 1 millivolt. Okay, so VI is okay. Now I will measure VR. Okay, I will measure VR here. Again, using the voltage probe here. VR is the voltage drop on the load resistance are the 3 here. VR. Okay, so VR in blue. So you should make a zoom to verify that there is a sine wave, and you can see here the amplitude here is around 160 millivolt. Okay, so 160. If you want to see to measure the VR exactly, you should left click on VR and it will display the cursor. It will display the cursor somewhere here. I will move around to find the cursor. Okay. The cursor is here. Okay, the cursor number 1. I will move the cursor around here to find the peak. Okay, the peak is here, and it will display the number here. In horizontal is the time. The time is here. Okay, it's around at about 7.36 milliseconds. I don't care. I just care about the amplitude. That means the vertical scale is 151.88 millivolt. So 152 millivolt. So if Vout is 152, Vin is 1 millivolt, so that divided by Vin, so I can deduce that the gain is 152, okay, from the simulation. From the hand calculation here, what is the gain from hand calculation? 151, okay, so very exact result, okay? So the error must be very small, so 152 minus 151 multiplied by 100 divided by 152, the error is less than 1%, so nearly perfect. Okay, your hand calculation and the simulation result verified each other very well, so it's very good. Okay, another thing to verify, so that is, so you can see here for the common emitter, you have to just verify the absolute value of the gain. So that is the 150. Okay. How about the minus sign here? Minus sign here indicate that the output signal is out of phase compared to the input signal. How can you verify that? Okay. So in this diagram, you can see that even if when you make a zoom, you can see only the Vout is a sine wave, but Vin it's just a straight line in green here. What happened here? The problem here is that if you display the Vin, which is 150 times smaller than Vout, in the same axis, Vin is so small that you cannot see the detail of Vin. You have to make a zoom here, and you can see that Vin is still a sine wave. But when you make a zoom for Vin, that means you cannot see the Vout because Vout is too big. Okay, so what can you do in that case? Okay, so in that case, I will display Vin and Vout in two different graphs. Okay, so each graph with its own scale, so that I can see the voltage differently. Okay, I just right click here. I think you can add trace as plot span. Okay, and in this plot span, you will display Vin. Okay, so you can see here Vin in its own scale from minus 1 millivolt to 1 millivolt. Vout in its own scale from minus 180 millivolt to plus 180 millivolt. And you can make a zoom here, the two graphs at the same time. Okay, voila, you can see that the output signal Vout is out of phase compared to the input signal. When the input signal is at minimum, the output is at maximum. And when the input is at maximum, the output is at minimum, right? You can see. So very good. You can do that at home. And at home, you can check. Let's say we have calculated that in order to certify the small signal configuration, the amplitude of Vin must be less than 5 millivolt, for example. So I will put 5 millivolt here and check again if it still work. Okay, so you can see here the input signal is still on-way sine wave, and the output signal is still sine wave. And I will check Vout. I will move it here until the maximum, the peak here. Okay, to verify its amplitude is 739, and divided by the input is 5, so the gain is still on way around 150. Okay, so what happens if the input signal is too large? For example, it's not 5 millivolt, but it's 100 millivolts, for example. Okay, so violate the small signal condition. Okay, so the condition for small signal here is Vi must be less than 5.5 millivolt. Okay, so here is Vi, we are checking with 100 millivolt. Let's see what happened. Voila, very interesting. Okay. Oh, you can see the input signal Vi 100 plus and minus 100 millivolts is still a sine wave, of course. But what about Vout? Is Vout a sine wave signal? No, it's distortion. Okay, so that means if you are singing to a microphone, you have a beautiful voice, you are singing very well with a beautiful voice, with beautiful song, but the that means amplifier that you are using is not good. That means at the output of the speaker, you will hear this very strange noise, and we call that the output is distortion. In Vietnamese, mèo giang, mèo. Okay, so the form of the output signal V out is not at the same form of the as the input signal V in here. Okay, because we are violating the small signal configuration here. Okay, and the gain is, of course, we cannot talk about the gain in this case. Okay, because the output is not sine wave. Okay, so you can see here at home you can play with that. Even I think that even when the amplitude is 15 millivolt, they're already distortion. Okay, so as you can see here, distortion. Okay, the VR is not sine. This closer the V in to the limit of the small signal model, the distortion is lesser. Okay, so 10 millivolt, quite still okay. The output is quite still still the sine wave, but you can see here it's not symmetrical because the maximum here is 1.5 volt, but the minimum here is about minus 1.8 volts. So that means it's not symmetrical. Okay. So that's advanced topic. We will talk about that in the next lesson in more detail. Okay. So, but it's already very interesting. You are lucky because for this code you can calculate by hands with using the procedure, applying the procedure and on the formula, and understand on the formula. And even when I change the name of the resistor here, you can still apply because you understand where it's come from the formula. You can deduce the formula yourself. And more interesting, that means you can simulate this circuit, okay, by this free LT Spice software to see the form of the input and output signal. I forgot. We run the simulation. If you want to verify the current gain, for example, you should measure the input current. Okay, so in this case, I will measure the input current here. The input current is the current supplied by the signal source. That means the current run through the internal resistance Ri. So I measure the current by using the current probe here. The current run through the resistor Ri. Okay, so you have the current I run through Ri is the input current here. You can see that it must be very small. Of course, it's the current at the base, so it's in the order of microampere. Okay. How about the output current? The output current I will display on this, and the output current is the current run through the load R3 here. Okay, so I will use the current probe here, run through the current here. Okay, so you can see here the current gain is about 15. Okay, because the output current is about 15 microampere, about 10, because the output current is about 15 microampere and the input current is about 1.8 microampere. Okay, so you can check the current gain also by taking the output current divided by the input current. Okay, so very interesting. You can verify at home. Of course, you can verify the terminal gain also by displaying the voltage at the terminal C and the input voltage at the terminal B, and take VC over VB to have the voltage terminal gain. Okay, cool. Any question before we stop? Okay, so we take a short break of 10 minutes. Then we will come back as 4:10 p.m. Okay.